more generalized kind of crash course in geomorphic analysis. So although I'm going to be demonstrating some of my own results of volcanic landscapes, many of the geomorphic analyses I'm going to be discussing are going to be applicable to all sorts of landscapes, be they volcanic, tectonic, passive margins, or even other planetary bodies. So for this talk, I'm going to start with a very brief introduction on landscapes. I'm then going to transition to discuss the various components of landscapes, as well as different metrics we can use to quantify them, and give some examples using Topo Toolbox. Afterwards, I'll discuss numerical landscape evolution modeling, again giving examples with Topo Toolbox, and I'll end with a very quick conclusion. So to dig right in, tectonic and volcanic landscapes undergo a series of processes that help drive their topographic form. In tectonic areas, such as the Himalayas, the main driver for this, of course, is surface uplift associated with orogenic growth. Whereas in volcanic landscapes, such as in the Cascades, background tectonic uplift is also augmented by volcanic processes in the form of volcanoes that are distributed throughout the landscape. These introduce various other processes, such as localized surface uplift associated with magmatic intrusions, as well as stochastic eruption events that generate material that mantles the topography and can either enhance or inhibit erosion. Looking at these two landscapes, we can start to see how these various processes impact the topographic form. For example, in tectonic landscapes, we can see that there's an overall high amount of elevation going between, reaching up to around 6 kilometers. Also, there exists a near linear drainage divide with a pretty consistent relief along the range. And finally, we can also observe a fully developed dendritic channel network throughout the entire mountain range. In comparison, if we look at the Cascades, we can see first that there's an overall lower amount of elevation, only reaching between 2 and 3 kilometers. Also, instead of a near linear drainage divide, we instead get this linear chain of singular peaks with an inconsistent relief. And these are associated with volcanoes of the arc. And finally, full drainage development is really only limited to the older volcanic zones, that being shown by the western parts of the Cascades. So the goal of geomorphology is to ultimately try to quantify these observations, also to relate them to erosion, and then eventually to interpret or estimate how these kind of landscapes evolve over time. So how do we do that? To dig right into it, it's worth first discussing the various components that exist within landscapes and what kind of metrics exist to quantify them. And it's worth saying that geomorphology has a very rich literature in terms of landscape analysis. In this talk, I'm showing some metrics that I'm most familiar with and have been able to collect over a few days, but there are many others that are well worth exploring. So those who are interested, I suggest really digging a bit more into the literature. So one of the first components we can think about is the actual topography of the landscape itself. And there's various ways that we can quantify this topography. One of the most basic examples is just to develop maps of the slope of various landforms. And this is an example of the Ericar volcano along the Andes, and showing the slope here in colors. And here we can more or less just see generally what kind of regions of the edifice have high slope areas versus low slope regions. Another, or an extension to this, is to look at slope aspect, which is to say the direction in which slopes are facing. And this is useful if we want to try to quantify how slope aspects relate to, for example, vegetation or erosion. And this is an example of that here from McGuire et al. 2014, which compares the northness of slopes to vegetation through the normalized difference vegetation index. And we can see that the more northward facing the slope is, the more vegetation exists. I should also mention this is of a cinder cone from the Springerville volcanic field in Arizona. And we can see an example of this through a satellite imagery of the cinder cone, in which the northern regions of the edifice have these drainages that are hosting spurts of vegetation throughout. A second metric that can be used is topographic curvature. Looking at both planform and profile curvature, this is a way of quantifying and distinguishing the different forms or different shapes that landforms can take on the landscape, being able to distinguish, say, basins from domes, from various saddles, as well as synforms and antiforms. And this could be used and applied to digital elevation model, DEM, to be able to distinguish ridges from drainage basins, for example. The third metric is topographic roughness. Here, there are multiple ways to calculate this, but one of the common examples is what's called the topographic position index. And all this does is calculate the difference in elevation between a cell of interest and the mean elevation of surrounding cells within some window size. And again, this is a way of being able to quantify different landforms. So applying this to aircar, for example, looking at a roughness window of 270 meters, we can start to pick out some features of the landscape, such as the ridges and the river channels. However, applying a 2-kilometer roughness window, we can start to see new features. For example, in the southeastern region, there exists a parasitic cone on this stratovolcano, which can be picked up by the roughness window. Finally, one last metric is to quantify landform length scales using signal processing. And this can be done either through Fourier transform, which calculates the amplitude or the power of specific wavelengths along the landscape, or by wavelet analysis. And this is completed through by calculating the coefficient between some wavelets at some size against topography. And it's worth saying that Will Struble gave a talk at this seminar just a few weeks ago and talked about this. So it's well worth looking at that if one wants to explore that a little bit further. Another component of landscapes are drainage basins or drainage catchments, shown here by the red regions. These also involve a series of their own metrics, including, in the simplest form, looking at basin lengths, widths, reliefs, orientations, and mean slopes. And here I'm just giving an example of what this kind of analysis would look like, again, for Aerocard, in which inside each of these panels, the various colored sections are drainage basins that exist on the volcano with the colors corresponding to each of the metrics. So, for example, we can see, looking at mean basin slopes, that of the basins that reach the edifice's summit, they all approximately have the same slope. However, the basins in the southeastern regions of the edifice have the highest lengths and widths compared to the others. A second metric, and kind of expanding on that, is to look at cross basin widths and heights. To do this, if we consider some sort of flow path through the drainage basin, at each pixel, we can calculate the distance to the divides, as well as the relief between the pixel and the divide. Doing that for Aerocard, we can generate this kind of cross basin width and relief map. And combining these, we can create what's called an incision index. It gives us some sort of quantification or idea of how much these kinds of landforms have eroded from some pristine natural volcano. Third in this list is what's called hypsometry or basin hypsometry. And this is a way of quantifying the areal distribution of relief within a drainage basin. For example, considering this kind of three-dimensional model of a drainage basin, we determine hypsometry at a specific relief of the basin by just calculating the amount of area that exists above that given relief. We do this for every elevation within the drainage basin, and then we normalize these values. We normalize the area by the entire basin area and the relief by the entire basin relief, generating this hypsometric curve. This is generally used as a quantity to define the erosional maturity of a drainage basin, in which young drainage basins have a hypsometric curve that are quite different from older drainage basins. And finally, one last metric to consider for drainage basins are area length relationships, or what's typically referred to as Hack's law. For this, drainage basins and their associated channel networks undergo or have a series of geometries associated with them. The most common geometry is what's called a dendritic channel network, and it's a kind of the leaf-like channel network that I think most people are familiar with. However, there's various other ones that exist, including parallel drainages, trellis drainages, and rectangular drainages. One way to be able to quantify these kinds of geometries is by simply taking the power law relationship between basin areas and basin lengths, shown here in this graph by the red line, in which the exponents of this power law what's typically called Hack's exponent, relates to the elongation of the drainage basin compared to its area. If the exponent is high, so if this red line is quite steep, it suggests more elongated basins. Whereas if the exponent is low, or that this red line is more shallow, it suggests more dendritic basins. And it's worth saying that in his initial study, Hack, who developed this power law, found in drainage basins on the east coast of the United States an exponent of around 0.6. And it's this value that's approximately considered then to be typical of dendritic basins. Moving on then, a third component of landscapes are river channels. And here there's a series of metrics that have been well explored across the various studies. Considering the channel network in planform view, a common metric is what's called drainage density. And for this, if we consider some drainage basin and an associated channel network shown here in red, the drainage density is just the sum of all channel lengths within the drainage basin divided by the drainage area. In this sense, higher levels of drainage density suggests that for the same area, there's higher amounts of channel networks existing on it. A second metric is an ordering scheme, and what's typically used is what's called a Strahler ordering. This is a way of using or of quantifying the magnitude of the drainage basin based on the different segments within the basin. So if we consider another drainage basin, where here we have the various river channels, what the Strahler ordering does is it looks at each segment of the channel and gives it some sort of number. So channels in the headwaters of the basin are given a first order number. Whenever two first order channels come together, they create a second order channel. And whenever two second order channels come together, they create a third order channel, and so forth and so on. This is ultimately a way of quantifying the topology of drainage basins and their associated, again, channel segments. For example, Ritter et al. 2011 demonstrated that at increasing channel orders, we have decreasing numbers of streams, but increasing channel lengths. Going a little bit further, a third metric is channel concavity, and what's also referred often as Flint's law. For this, if we consider a longitudinal profile of the channel network, we can often observe that it has some sort of concave feature to it. It curves upwards as it expands elevation. This is a metric that can be easily quantified. The simplest way of doing this is simply calculating the power law function between upstream drainage basin area and local slope for every point of the channel network. Doing that creates an approximately linear line, an approximate line in log space here, in which the slope of that line is what's referred to as the concavity index, and is typically used and is typically referred to as the theta term. Expanding on that a little bit more, the final metrics considered for river channels are Nick points, KSN analysis, and a chi transformation. Going back to longitudinal river profiles, we often observe that there's an abrupt change in concavity that exists within the profile. And this is also usually picked up in the power law between upstream drainage area and local slope. These abrupt changes in concavity are what we refer to as Nick points. And the simple way of kind of visualizing this, if you were standing on a landscape, is to think of a waterfall, for example. That's a typical example of a Nick point. Various processes can generate Nick points. For example, it could be caused by changes in lithology along the channel network, in which case this Nick point becomes pinned to that lithologic boundary and moves as the boundary moves with the channel eroding. Alternatively, another way Nick points can form are through abrupt changes in either erosion or uplift on the landscape. So if the landscape undergoes an increased amount of uplift, some Nick point will form at the base level and then begin to migrate upstream. And this generates a new state within the drainage basin and also the channel network then. So this is a way of kind of looking at the various states that can exist within landscapes. Upstream of a Nick point, in this kind of regard, are the previous states of the landscape, whereas downstream is the new state. One way in which we can quantify where nick points are, and I should mention, this also exists across an entire channel network. So for example, if we take channel profiles of a network in the Rowan Plateau in Colorado, we can observe multiple nick points that exist at every channel segment. These are essentially tied to some elevation, but exist at different distances upstream of the base level. So one way that we can quantify the occurrence of these nick points is by incorporating what's called the stream power law, shown here on the right side of the equation. The stream power law is a semi-empirical erosion model for how rivers evolve, in which K is some sort of rock erodibility, A is upstream drainage area raised to an exponent M, and S is local slope raised to an exponent N. We then put that into what's called the general landscape evolution model, in which the change in elevation with respect to time equals the amount of uplift, the rate of uplift, minus the rate of erosion. From this model, from this equation, we can start to play some numerical games to change or rearrange the equation. For example, we can begin by assuming a steady state topography. That is to say that uplift and erosion are equal everywhere. This basically sets the left side of the equation to 0. And from that, we can rearrange the equation in this form, with slope on the left and drainage area on the right, as well as this kind of coefficient between uplift and erodibility raised to 1 over n. You might recognize that this is very similar to Flint's law from the previous slide. And this is essentially how we can kind of quantify nick points. By assuming some sort of reference concavity index, we can derive what's called the normalized steepness index, or KSM. And this is a quantity that we can then use across all river channels within a channel network to see which regions of the channel are steeper compared to what we would expect from the concavity index, shown here by the red lines. And these are generally, these could be associated with nick points. An alternative approach is to do what's called a chi transformation. Using the same equation, but here we take the slope, and instead of keeping it as its own quantity, we expand it to be dz over dx, so the change in elevation with respect to space. We can then rearrange this equation by integrating across elevation and distance, creating this long equation here. Going a little bit further, if we incorporate some sort of reference drainage area, we can create what's called the chi transformation. And this is essentially the integral of drainage area as you move along a river channel. What this ultimately does is it removes the concavity of a drainage channel. So we take if we consider a typical channel profile, it has this kind of concave feature. Applying a chi transformation turns the horizontal distance into this chi term, which creates a linear profile within chi space if the landscape is in steady state. This is also a way of comparing different channel networks across a region. And to give an example of this, if we go back to this channel network on the Rowan Plateau, although we have these nick points existing at the same elevation, but different distances upstream, if we convert this horizontal distance into chi space, we can see that the nick points more or less collapse down into a single location. So again, this is just a way of helping to better quantify or understand channel networks by removing the concavity. Finally, the last component to consider are drainage divides themselves, shown here. And here there are also a variety of metrics that can be used. First is to look at divide ordering, distance, and elevation. So for this, if we go to a typical landscape, we can essentially assume that the network of drainages can be analyzed the exact same way that you would analyze a channel network. And this way, you can generate a Strahler ordering of the divide network, as well as calculating the distance, the divide distance from the highest topography, and then run any kind of analysis to understand how these divides might relate to various other metrics. Another approach is to determine divide migration between basins based on cross-divide metric differences. Kind of common example of this is to look at the differences in chi between drainage basins. And in the study that kind of introduced this, Will et al. 2014, they postulate that if you calculate chi between two basins that share a common divide, and if this chi value is different between the divide will migrate towards the higher chi regions and will continue to migrate until chi becomes equal. This was also demonstrated by them using numerical modeling, in which here they set some sort of tectonic tilting to cause the divide to migrate towards the north, and then set the uplift back to a uniform amount so that the divide would migrate towards the south. And here, calculating chi, in this regard, we can see that higher chi values exist on the southern portion of the drainage divide, suggesting that the divide will actually migrate towards these channels. This was also expanded on then by Whipple et al. 2017 to also look at cross-divide differences across the divide between channel elevations, headwater reliefs, and headwater slopes, defining these same kind of behaviors as the landscape evolves. And as kind of a last metric for this, these were simplified to some degree with the divide asymmetry index by Schirler and Schwenghart 2020, which simply calculates the difference, or sorry, the absolute difference in hill slope reliefs across the divide, and then divides it by the total hill slope relief. So this generates a normalized value between 0 and 1, in which 1 represents a divide that's most likely to be mobile and thus migrating. So from all these metrics, there are a variety of programs that can be used to analyze DEMs through all these different metrics I just discussed. Kind of the typical programs that I know a lot of people use are things such as ArcGIS or QGIS. And these are GUI-based softwares or generated user interface softwares that allow mouse clicks and various visualizations of the data. Also, it's worth saying that each of these have some sort of Python core that you can use to also script within these if you wanted to. For those who prefer kind of more old school methods, there's what's called the generic mapping tools, which is a more Unix-based mapping software and analysis software, which has recently developed a MATLAB wrapper. Other softwares include LSD Topo Tools, which is both a GUI and a Python based program, and then finally Topo Toolbox that's developed in MATLAB. For this talk, I'm going to be focusing mainly on examples in Topo Toolbox. And if anyone wants to explore Topo Toolbox or download it, it's available from Wolfgang Schwenghart's GitHub. Look at this address. And there's also a pretty extensive blog archive on Topo Toolbox's WordPress that give examples of how to use the program to perform a variety of analyses. So to dig into how Topo Toolbox works, Topo Toolbox analyzes the landscape through a series of structures or objects. These include, for example, the grid object, which basically stores the DEM and allows for a variety of DEM processing, such as reprojecting the DEM, resampling the DEM, or cropping the DEM. Also, different map visualizations, as well as being able to calculate metrics such as slope, curvature, and roughness, and also a variety of other functionalities. Slope objects essentially store the flow direction of the topography, and these can be used to derive drainage basins, calculate upstream drainage areas, or extract flow paths. Also along this line are stream objects, which store the channel network, and this can be used to determine drainage density, different stream orders, derive channel profiles, conduct slope area analysis, KSN analysis, chi transforms, as well as finding nick points that exist within the channel network. And finally, are divide objects, which look at, again, the divide network, keeping quantities or keeping analyses such as the divide order and distance, as well as the distance and elevation of divide junctions, where 3 or more divides come together, and also calculating the divide asymmetry index. So to give an example of how Topo Toolbox works, I'm just going to give a really brief introduction from a script I made that will be used to analyze some of the drainage basins around Mount Hood in Oregon. And I'll mention I didn't get the chance to share this script before the talk, but I loaded all these scripts into my Google Drive, and I'm happy to share the link afterwards for those who want to explore this further. So to run Topo Toolbox, we need to start with the TIFF file, or the path and location of the TIFF file for the DEM. And here I'm just using a TIFF file that I made for Mount Hood. We also needed to find the grid resolution that we're going to resample the grid to. And here I'm going to assume a 60-meter grid resolution. So in MATLAB, all we need to do is run or call the grid object function, passing to it the TIFF file. From here, Topo Toolbox automatically imports the data into its mainframe or its structure. Other functions that we could run on this are to resample the grid to the 60 meters or any other kind of resolution one wants. And although it's not required, sometimes recommended is to call this fill sinks function, which will fill any holes within the DEM and ensure that the drainage network is able to reach the grid boundaries. And then the rest of the script is just used to create the figure shown on the right. Going a bit further, we can then derive the channel network around Mount Hood. To do this, we first create the flow object by just passing the DEM. And from that flow object, we call the stream object by just passing the flow object, as well as some drainage area, minimum drainage area for channelization, which here we assume to be 5 square kilometers. And finally, these last arguments are just to tell the function that we are using map units for this minimum area. So the result of that is the figure on the right, which shows the topography in colors, and then the black lines here are the channel networks that Topo Toolbox was able to determine. Going further, we can look at the stream order that exists within these channel networks, and this is just a single function called stream order, where we pass the stream object. Plotting that, then we create this gray hill shape, and then the various lines now have these colors that relate to the stream orders. Using that, one of the last things I wanted to demonstrate is how to derive drainage basins and extract channel networks to these basins. So for this, we start by calling this function drainage basins. And this is just used to create a grid object of drainage basins. We pass the flow object to it, as well as a grid object of the Strahler orderings. And finally, this last argument, which tells the function which order of basins we want to analyze. And here we're going to look at order 3 basins. The last lines here are just used to help rearrange the basin ID numbers and to remove any kind of background basins that we don't want to worry about. So on the right, we can observe what these basins look like then. And again, these are 3rd order drainage basins that exist around Mount Hood, where the colors are just some unique identification number for that basin. Going further, we can then extract the channel networks to each of these basins. To do that, we just create a new DEM based on the old DEM, and here we remove all the topography that exists outside of our drainage basins. From that, we call the flow object again, as well as the stream object, and that will then create this extracted stream network. And here you can see that the network is really just constrained to these 3rd order basins that we wanted to analyze. From here, we can run any number of analyses that we wanted to based on the metrics that I kind of showed before, including, for example, drainage density, also a chi analysis, and even a divide analysis. A divide asymmetry index analysis. Here I kind of briefed over these just for time, but this shows kind of in a really quick manner how we can use Topo Toolbox for very basic analysis. And we can then use these results to expand on those and look at new metrics that are kind of outside the scope of Topo Toolbox. One last thing I'll say about this is another advantage of doing landscape analysis in this manner through programs is that the results are easily reproducible and creating a generalized script, we can then make an automated function that can be used through multiple iterations. So for an example of that, I recently created a software package or scripting package called DrangeVolc, which builds off the Topo toolbox and is designed to analyze drainage basins that exist specifically on volcanic edifices. This essentially has the same functionality as Topo toolbox, in which we start with a DEM of the volcano, as well as some sort of derived edifice boundary, and then it performs a series and automatically performs a series of analyses that we discuss, including Heck's law, also looking at the number of basins that exist along each contour of the edifice, as well as basin hypsometries, basin lengths, basin widths, mean basin slopes, basin reliefs, also calculating the divide asymmetry index. Using this package for 12 volcanoes from Indonesia, Papua New Guinea, and New Zealand, what we were able to find is that the majority of these drainage metrics correspond really quite well to the age of the volcano. So here I'm giving an example of that, which the x-axis is volcano age, shown here by the points, and in each subplot, the y-axis is the different metrics. So what we can see is that there are some pretty good temporal trends for drainage density, summit basin hypsometry, summit basin length, and summit basin width. Specifically, we can observe that drainage density decreases as the edifice gets older, hypsometry increases, basin lengths decrease, and basin widths increase. And this is pretty exciting because it suggests that we can get a rough estimation of a volcano's age of activity based purely off topography, which allows for some very quick remote sensing analysis of volcanoes. So now that we've discussed these analyses, I'm going to switch gears a little bit and talk about landscape evolution models. Just like before, there are a variety of models that exist and communities that use those models. Three of the most common I know of include LandLab, and this is from the Community Surface Dynamics Modeling System. LandLab is mainly Python-based. Second model is what's called FastScape from the German Research Center for Geosciences, which is both Python and Fortran-based. And of course, Topo Toolbox has its own landscape evolution model built into it. And it's worth saying that there are many others that various researchers have made throughout the years. So to give some examples for Topo Toolbox, well, I guess to back up a little bit and speak broadly about landscape evolution modeling, even though I discussed it a little bit before, the general equation for landscape evolution simply assumes that the change in elevation with respect to time equals the rate of uplift minus the rate of erosion. So if we consider or think about some landscape, we assume that the landscape is uplifted by some amount, and in response, various erosional processes work to remove material. In a very basic landscape evolution modeling sense, we can separate the regions of the landscape into two main regimes, hill slopes and river channels. A very basic model that's used for river channels, the one I discussed before, is the stream power law, which relates erosion, E, to a rock erodibility, as well as precipitation scaling and upstream drainage area, both raised to an exponent m, as well as local slope raised to an exponent n. For hill slopes, a very basic model is a linear diffusion model, which relates erosion to a soil diffusivity parameter, as well as the divergence of topography. And again, it's worth pointing out that these are very basic models, and there are much more sophisticated models that exist. For example, there are different variations of the stream power law that look at sediment deposition within river channels, or assume some sort of threshold for discharge to allow erosion to occur. Similarly, hill slope models include something like a nonlinear diffusion model that accounts for steep terrain, as well as a variety of landslide or debris flow models. So regardless of what one uses for their erosional laws, though, there are a variety of parameters that need to be established in order to run a numerical model. These include grid parameters, forcing parameters, as well as erosional parameters. For the grid parameters, this includes some sort of grid resolution, also the limits or the extent of the grid, and finally, what kind of boundary conditions exist along the grid edges. Is the grid edge kept at constant elevation? Do we allow different material to come into the grid or out of the grid? These kinds of aspects. We also need to set up a model time step, as well as the total runtime or total time that we're going to be running the model. And if desired, the time steps in which we're going to be saving the model results. Finally, every model requires an initial topography. This is an initial condition, essentially. In terms of forcing parameters, this usually involves an uplift function, and in the case of orogenic growth, some sort of tectonic short function. Finally, for the erosional parameters, for the stream power parameters, this includes some sort of numerical scheme. It's worth saying there are various ways in which these erosional laws can be discretized numerically, and each of these schemes have their own amount of error and their own stability, and as well as conditions in which models become unstable. So we need to be able to define that. We also need to set the erodibility, precipitation, scaling, and area and slope exponents. For hill slope parameters, we also, again, need to set some sort of numerical scheme, as well as the soil diffusivity value. And finally, in the case of landsliding or the nonlinear diffusion case, some sort of slope threshold, as well as other parameters if different forcing and erosional laws are used. So just like before, I created a very simple example for how to use Tobal Toolbox to create a numerical model. And for this, basically the model is ran with a single function called ttlem. This takes on three main arguments. The first argument is a grid object of the initial topography. So again, our initial condition. The second argument is a grid object of the uplift function. And finally, the third argument is the model parameter structure. So just to give some code snippets here, for the initial topography, I'm just creating a model domain that is 60 kilometers in the x direction and 30 kilometers in the y direction. It has a grid resolution of 60 meters. And I just go through to create a uniform initial topography that's 10 meters in height. And I seed that topography with some random white noise that will help drive convergence, flow convergence. For the uplift function, I'm just going to assume a uniform uplift rate of 1 millimeter per year. And again, just create that grid and then convert it into a grid object. And then finally, for the model parameter structure, this can be created through a function called ttlem set, which is a built-in Tobal Toolbox function that automatically creates the entire parameter structure for the model. But we can then go through and change some of the parameters. For example, I want to use a linear diffusion equation scheme. I also want diffusion to occur within river channels. I'm also going to set our erodibility parameters, soil diffusivity, and precipitation, normalized precipitation value, just as constant values, ranging or going being 10 to negative 5, 10 to negative 2, and 1, respectively. And finally, I set a total model time of 20 million years with 100,000 year time steps and save every other step. So to give an example of how the script produces the model, this is essentially the model time steps through the 20 million years. And we can see in the beginning couple million years that drainages are quickly developed and begin to incise into the landscape. For the most part, the outer regions of the landscape are already in steady state, but you'll notice there's an amount of divide migration occurring in the center regions. This is because the topography is trying to reach a steady state. And again, that's where uplift and erosion are equal everywhere. This requires drainage basins to expand or contract in order to adjust their drainage areas and slopes with their neighbors to accomplish this steady state. So after running this for 20 million years, this is the final result. We can go a little bit further then and try to start looking at how different parameters impact landscape erosion or landscape evolution. I do this through three main scripts and incorporate an uplift gradient, a precipitation gradient, and a lithology gradient. For each of these scripts, I use the output from the base model as our new initial conditions. So for the uplift gradients, I'm just going to assume a gradient that goes from the west side of the grid to the east side of the grid, in which the west side of the grid has an uplift of 1 millimeter per year, and the right side has an uplift of 5 millimeters per year. For the precipitation gradient, I'm also going to look at this east-west direction, in which the west side of the grid has a scale of precipitation of 0.1, and the right side has a precipitation of 1. So the majority of precipitation occurs on the eastern side of the grid. And finally, for the lithology, I'm going to look at erodibility differences in a series of steps going from south to north of the grid. And this is going to be using values ranging from 0.5 to 1 times 10 to the 5. So just a half of an order of magnitude. So real quickly to run through these results, starting with our uplift gradients, we can see almost instantaneously that the higher amount of uplift on the eastern side of the grid causes a high amount of elevation to form. We can also observe that the majority of drainage divides begin to migrate towards this higher elevation, or sorry, to this higher uplift rate. And here I'm only running these models for 10 million years. In comparison, looking at our normalized precipitation model, we can see the opposite effect. By increasing the precipitation on the east side to the west, we essentially form our highest amount of elevations in the western part of the grid. And similarly, we can see that divides begin to migrate towards that side. And finally, looking at our erodibility gradient from east to north, we can see a similar kind of behavior in which the regions in the south have the higher erodibility and thus erode the fastest, leaving behind a higher elevations in the northern parts that don't erode as quickly. And thus, we see the entire drainage divide migrating towards that region. So just comparing the results of each of these models, we can begin to see how the parameters begin to impact model behaviors and thus landscape evolution. Now, I'll say these are very, very simple examples, but they give the foundation for which more sophisticated modeling studies can be used. To give examples of these, for example, Braun et al. 2013 analyzed channel network response to dynamic topography sweeping across the landscape. In comparison, Whipple et al. 2016 looked at the occurrence of high elevation, low relief surfaces in response to channel piracy or an increased amount of uplift within the landscape. Similarly, Fox et al. 2014 combined landscape evolution forward modeling with inverse modeling in order to try to analyze and interpret the tectonic history of Taiwan. And finally, McGuire 2014 looked at differences in erodibility and soil diffusivity between northern and southern portions of cinder cones to look at how these derive different cinder cone asymmetries. And of course, there's many, many other examples. So to very quickly wrap up, in a very generalized sense, various analysis programs exist that provide powerful tools to quantify landscapes over a range of scales. These include ArcGIS, QGIS, LSD tools, GMT, as well as Topo Toolbox. And these different range of scales include looking at topography over the entire landscape, as well as channel networks, drainage divides, and drainage basins. Also, numerical modeling further enhances these analyses by simulating landscape evolution over longer timescales. And for example, I gave some previous examples using Topo Toolbox. And just to quickly wrap up with some bookkeeping, the scripts for this talk are loaded up onto my Google Drive, and maybe I can paste this link into the chat so people don't have to worry about trying to type these random letters into a web browser. Also, Topo Toolbox can be downloaded from, again, Wolfgang Schwinghart's GitHub. The scripts to analyze volcanic edifice morphologies that I discussed, that being drainage volc, are available from my own GitHub, and the accompanying paper is currently shown as a preprint or uploaded as a preprint to eSurf if anyone wants to explore that. Finally, I'll say that I'm always happy to discuss landscape evolution or any kind of metrics for quantifying landscapes, so feel free to shoot me an email if you have any questions. Thank you.